Okay, now, as we discussed before, we will cover several concepts in graph theory, and one of them was matching. Recall that the following job assignment problem was a good motivation for studying the concept of matching. One of very natural problem where we want to use graph are this job assignment problem. There are like jobs, say 1, 2, n, and like there are many sets of applicants. And each jobs and candidates, you can consider that for each job, there are certain set of people who are qualified for this job. It is not everyone, but there are a set of people, say, people in A1 are qualified for job 1, and people in A2 are qualified for job 2, and so on. Then what's the, typical situation in this case? In each job, we want to hire people. Among these qualified people, you want to choose the people who will do this job. But we want to make sure that each job, you choose one applicant who will do this job, and each applicant will do only one job. This is full-time job. Then what's the typical goal? We want to find, say, xi, which are in AI, for, say, each of this I in bracket n in a way that they are all distinct. So we want to choose the element x1, x2, to xn, so that they are all distinct, they are all different. And xi belong to AI. And this is called a system of distinct representative, and or simply SDR of the sets A1 to AN. This is exactly what we describe. It's a, say, the set of distinct element x1 to xn such that, when I write s dot t dot, it usually means such that each xi belong to AI. And there is natural way to consider graphs in this problem. And how do we do this? Is we consider the following concept. We consider the incidence graph of this family of sets AN is defined to have the vertex set as the partite set. On one part you have a script, the bracket n, 1 to n is on one side. And the other one is the union of this AI, all possible elements in the set AI, who are the applicants. And we make the X and where X and I are adjacent if and only if X is in AI. This gives you a graph which has this bipartite structure. So this gives a bipartite graph. And in here, how does this system of distinct representative looks like? This one is matched with x1, and this one is matched with x2, and 3 is matched with x3, and n is matched with xn. So we get this. Okay, maybe not every job is filled. So it could be that 3 is not actually matched to anyone. Oh, no, sorry. In the system of distinct representative, this definition requires, every job is filled with an, eligible applicant. So this is what the system of distinct representative looks like. As a graph, these blue edges give you a subgraph, which looks disjoint edges which are pairwise non-incident. And systems of distinct representative requires all the elements on this top is covered. Maybe some applicants didn't get picked, but this has to be all picked. So this example of this natural problem gives us the motivation to define this graph. Looks like this. The disjoint edges, set of disjoint edges. So we give a name of matching to this subgraph. The matching, because it's matching a job and candidate, right? A matching in the graph G is a set of pairwise non-incident graph edges, meaning that the two edges does not share a vertex, which is also sometimes called independent edges. And we want to define certain language, certain terminology, so that our discussion later will be, more efficient. And we say that a matching covers the vertices in its edges. So this matching covers all these vertices. We will say that, but if there is some vertex which is not incident with any blue edges, so this is not covered by the matching. And we say that if there is a matching that covers all vertices of a G, is called a perfect matching in G. And we define the matching number, and let's write down alpha prime of G is the maximum size. Here size is the number of edges of matching in G. So before, the independence number was alpha. And then here, we have alpha with the prime. And usually this prime indicates that we are defining parameter related to edges. And here it's about the independent edges. So alpha is like independent. It's related to independence. And then prime is related to the edges. So we give this definition. Okay, so now our goal is to study about this matching. When can we find the perfect matching? And if we cannot find the perfect matching, then can we find the large matching? What's the size of the largest matching? Can we find the alpha prime of G? And first, what we want to do is we want to study about the matchings in bipartite graph first. As we saw this natural problem of Java assignment, which also can be formulated in different way. You can consider this as not job and applicant. You can consider this as any other object, like resources, and you want to distribute the resources, or other scenario. You can, consider, other type of the problem, which is essentially same. So here, the graph structure you get is bipartite. So it's natural to consider the matchings in bipartite graph first. Okay? And so what's the question? Question is that when does say XY bipartite graph, whose one part is the set X and the other part is set Y, when does it have a perfect matching? This is natural question. And for that, let's define one terminology for a vertex set S. We write N over S as the union of the neighbors of all vertices in S. So let's write this. So for example, if you have this graph, so in general, it doesn't have to be in bipartite graph. Then if you take this, then you take the union of neighbors. Then the first vertex this, second vertex this, third vertex this. So this end of S is everything but this one vertex. So that was just one example. Anyway, so this definition is clear. So oftentimes we want to find some sufficient condition for certain property. What we do is we try to see what are the necessary conditions for that. And then some of the necessary condition, we are hoping that that is actually a sufficient condition. Then we get the necessary and sufficient condition, which provides some characterization of the property, characterization of the objects which satisfy our desired property, which is very satisfying case. So here, what is some obvious necessary condition for the perfect matching? So if you have this perfect matching, in here, let's say this is X, this is Y, and no matter what S we take, which is subset of X, neighborhood of X neighborhood of S. So there could be other edges which are not part of this perfect matching. Then this N of S always contains their counterpart. So each of them has a counterpart through this blue edges, the perfect matching. And N of S is here, which contains all of its counterpart. So what we know is that this set is always bigger than or equal to S for all S which is subset of X if it has a perfect matching. So this is one of the necessary conditions. And the following theorem, known as Hall's theorem, shows that this condition is not only necessary, but also sufficient in bipartite graph to have a perfect matching. If you have XY bipartite graph, we know that there exists matching covering all vertices in X if and only if this neighborhood of S is as big as the set size of the set S itself for all S subset of S. Again, we were talking about perfect matching, and for the perfect matching to exist, the size of X and size of Y must be same. Otherwise, perfect matching does not exist. So in such a case, you consider the X as one of the parts, then its existence of a matching covering X is same as a perfect matching. So this is actually slightly more general than just a perfect matching. When X is smaller and Y is bigger, it still gives us a characterization of the graph which have the largest possible matching. So this give us a pretty satisfying characterization of the graphs with the maximum possible matching if the graph is bipartite graph. So let's prove it before discussing more about its consequences. So this direction, the necessity direction, is easy. We already have discussed it here. So only thing we need to actually prove is this direction. If this is called Hall's condition. If Hall's condition holds, then can you find the matching covering X? Yeah, this is what we want to prove. Then we use induction. There are several proofs, but let's use induction on what? Size of X. So if this has what size 1, if X has only one element, then the claim is obvious. What does it mean? You have only one element in X, and then there is at least one edge going out, and you just choose one edge, and that's it. It covers X. It is a matching that covers X. So we assume X is at least 2. It has at least 2 elements. So what kind of induction can we use? So our goal is to partition this X into two graphs, and then you want to find the matching covering X, this part here, and the matching covering this part here using induction hypothesis. Then that will be, pretty obvious approach to prove this using induction. So this is our goal. And one pretty obvious case is that if we say take a one edge and then delete it, and remaining one still satisfy the hold condition, then you just apply induction on here. Then together with this one edge, it will be good, right? But when is that case? So in order for this remainder of the graph still satisfy the hold condition after deleting this one, the original one must have satisfied the hold condition with additional some margin. So if it's satisfy hold condition in a stronger way without equality here for every non-empty subset S. Okay. Technically non-empty proper subset X. S. So obviously in the empty set S, if both are zero, so it's equality. And then if S is everything, then it's also, could be equality when X and Y have the same size. Remember, our goal was to partition into two, so it could be both of them has to be non-empty. So here again, this is partition of two. One set of size one on both parts, and then set of size one less on both parts. And in that way, we don't want any parts to be empty or everything. So in that case, then what? Then we choose arbitrary element x in x and y in the neighbor of x. And this exists as n of x has size bigger than 1 by Holt's condition. So we choose this. Then we consider the graph G minus these two vertices. You just delete those two vertices and then all the edges incident with it. Then this graph satisfies Holt's condition. Because what? For all S in here, if you consider the set of neighborhoods of S, this lowest and most one element Y. So this condition, now deleting by one, meaning that the induction hypothesis. Yeah. So this condition, and then you delete by one, implies that in this graph, corresponding satisfied with the possible equality here. And what do we get? So induction hypothesis. So IH, if I write it in, means induction hypothesis. Here's that what? This is a graph whose x part is smaller than the original graph. So whole theorem, this theorem must be true for this smaller graph. So it yields a matching covering x minus element x, and the hxy together with this matching completes the desired matching in G. So this case is done, but otherwise there exists a set S which satisfies equality here for some non-empty proper subset S of X. And what do we do? Now, we take S as this part. So let's say G1 be the graph induced by S and its neighborhood set. And let G2 be the graph, the remaining graph. So induced by everything outside. So you have S and then N of S, which has the same size. This is G1 and this is G2. And then we want to apply induction hypothesis on both graphs to complete the matching. But holds condition holds for, say, G1. It's obvious. So whatever S prime you take here, which is subset of S, its neighborhood set has to be at least as big as S prime because of this just condition for the original graph. It's just the induced subgraph of it. And this does not send any edges to outside. Its neighborhood in the original graph is totally contained in here, so which is not lost in this induced subgraph. And we want to check holds condition for G2, what? For each set, say T, right in here, we want to check its neighborhood is as big as T. What do we have? We have that its neighborhood in G2. So it could that it's sending some edges here and then it's also sending some edges upward. So this is same as what? You take everything here and take the neighborhood S union T. Remember that this part only sends the edges here, so it doesn't send any edges on the bottom part. There is no such edge exists. And you subtract the neighborhood of S. These two are same. Then what do we get? So the size of neighborhood of T in G2 is same as you take in the original graph, you take S and T, and then you take the neighborhood, and then you subtract this. But the original graph satisfies the holds condition, so this set is as big as S union T, and by our choice, this equality holds. So this set has size S, which is size T. So this neighborhood of T is as big as the set T itself. So by induction hypothesis, so it is G2 also satisfy the holds condition and G1 satisfy the holds condition. Both of them are smaller than G. So induction hypothesis implies that each of G1 and G2 has a matching covering S and the remaining X minus S. So hence their union is the desired matching covering X. That proves the theorem. So we prove this whole theorem, and then this gives us some further applications. Maybe, yeah, before talking about the alpha prime of G, which is the size of maximum matching, maybe we talk about marriage theorem first. This Koenig's says that every non-trivial regular bipartite multigraph, so it doesn't have to be simple graph, it has a perfect matching. So if you have a bipartite graph, it doesn't have to be simple graph, it could be multigraph. Of course, bipartite graph doesn't have a loop. It could be only have a multiple edges. And it is not trivial, means that it has at least one edge on both sides, and then there are edges between. At least one vertex is on both sides, and at least one edge there. And then if it is regular, meaning that every vertex has the same degree, then it has a perfect matching. It was called Merry theorem when they proved this, but perhaps, I mean, this is no longer like a good name. I mean, for one, I mean, other condition, okay, but these two conditions are regular, so everybody have the same degree. It's not really true in marriage situation, right? Some people have a higher chances, and some people have less chances with many more people and less people. And also, bipartite is no longer true. I mean, at the time, they were thinking that men on the one side and then woman on the other side, but now, I mean, the marriage or dating are not between two genders. So this is outdated name. But anyway, so this theorem can be proved using Hall theorem. So let's say K is at least 1, and we consider a K regular XY bigraph, bipartite multigraph. And what we want to do, in order to prove the existence of perfect matching, we want to show that it satisfies Hall's condition. Okay, to be more concrete, I mean, if we have a K-regular bipartite graph, then it's easy to show that, check that X and Y have the same size. But, and which is not really required, as the following lines actually implies that. So if you consider S in X, and you choose X as the bigger or equal part out of these two parts I said, X is bigger or equal part. So you assume X is bigger than or equal to Y. And for each S, which is a subset of X, say, for each is what we count the number of edges between S and its neighborhood of S. Then what we get? Each of the vertex in S has degree K, which is sending K edges. And all of them are going to N of S. On the other hand, N of S may send some edges outside. So it's sending K edges. So these blue ones are here. And what? If we count all the edges incident with N of S, this red part is what? Almost K times size of n of s. So that's, again, each vertex here has degree k, so you count k for each vertex. And then this counts all these blue edges, as well as something, it might count more. So this inequality holds. Then, as k is at least 1, it is not 0. This implies what? False condition. So false condition holds. So false theorem implies that it has a matching covering X. And X was the bigger or equal part. So it shows that it has a perfect match. So this was one application of the whole theorem. And moreover, we can use this to prove the following. So when we want to check whether a bipartite graph has perfect matching or not, this provides one criteria that we can use. And what if we want to find the maximum matching? When we have a graph which does not have a perfect matching, but we still want to find the biggest possible matching. Then we can actually reduce our problem to a smaller problem, to another problem where the finding perfect matching in another problem is same as finding biggest matching in the original problem. Then we actually get this statement. So if we have XY bigraph G, then the maximum size of matching in G satisfies. So that's how we write alpha prime of G. So this is minimum out of all choice of S. You take X, and then you subtract the difference between S and neighborhood of S. So what does this measure? This measures when we have S, then sometimes this n of S is smaller, but the smaller by how much you try to maximize this, then you can minimize this. And then that gives you the, size of the maximum matching. So let's prove. So this inequality is easy because if you have S and then n of S for whatever S you take, and all the edges are actually going from S to here, then no matter how you take your matching, these red vertices are not going to be matched because you have like 5 vertices here. Only 3 of them are available, then 2 are missed. So you know that every matching is at least S minus n of S vertices of S for whatever choice of S. So alpha prime of G is n most this expression. So let's prove this part. We let the D be this maximum value of this deficiency between S and NS. So when S is here, you take a neighbor, what's the difference? So you try to maximize this. And let's say T is the maximum. And we will construct. So it suffices to construct matching of size x minus t. Say we want to. So if we construct such a matching, then we win, right? This is size of maximum matching, and we just construct one matching with this size. So maximum matching is as big as the matching that we just constructed. So what do? We have x and y, and we add some artificial vertices. We add the new vertices to y and make them adjacent to all vertices of x to obtain a new graph G prime. So these are all adjacent. Now what? Now this G prime has a matching of size x by whole theorem. Why? So this much was added. So for neighborhood of S in G prime is size of neighborhood of S in G plus D. And due to this, what do we get? This is at least size of S. This is one specific S, and then this is maximum out of all S. So you get that. So by whole theorem, you have a matching covering X. And at most D edges of this matching are in G prime minus G, so which is additional artificial edges we add. So the remaining edges form a matching of size x minus d as desired. So this proves the theorem. So we have shown a necessary and sufficient condition of a bipartite graph to have a perfect matching. And we use it to find the formula for the size of maximum matching. So matching number, alpha prime of G. So yeah, matching number. And also we saw a corollary of whole theorem, which says that every regular bipartite multigraph has a perfect match. So this proof, I mean, I didn't mention it, but even if there are multiple edges, so every proof still works. Okay, in next video we will study about the relationship between this matching number and some other parameter which has natural relation with this matching number.